A mysterious object streaks through the void, drawing the attention of the world's leading scientists. One Harvard professor dares to suggest it may not be a comet at all, but a fragment of alien technology. At unimaginable speed, it races toward the sun, carrying ice older than the Earth. Born in the distant fire of another star system billions of years ago, telescopes have captured its arrival, revealing a traveler whose velocity defies every known record. This ancient shard of dust, small as a teardrop, is reshaping our understanding of the space between stars. It is the third confirmed visitor from beyond our solar system, a wanderer that has been journeying longer than life itself has existed on our planet, arriving now at this singular moment. The universe has sent a messenger, and we are ready to hear it. High above the desert skies of Chile, a robotic telescope swept its gaze across the stars, searching for hidden dangers that could wipe out civilization in moments. But what it uncovered was far stranger than a killer asteroid. It was a discovery that would challenge everything we believed about visitors from the deep cosmos. The instrument, part of the Asteroid Terrestrial Impact Last Alert System, caught sight of a dim speck moving against the fixed lights of the heavens. Yet this faint intruder refused to behave like any asteroid or comet astronomers had ever seen. Instead of flowing along the familiar currents of our solar system, it was cutting straight across them, heading in from the wrong direction entirely. Picture our solar system as a great whirlpool, with the sun pulling planets and debris into steady, predictable motion like leaves drifting along a stream. Every object born here obeys this flow. But this wanderer was defying the pattern, surging upstream, unbound by the sun's grasp. From the very first hours of observation, scientists realized they were facing something extraordinary. Where most space rocks drift at speeds of thousands of miles per hour, this traveler was blazing so fast that it seemed to outrun not only our solar system's gravity, but even the pull of neighboring stars. The revelation struck the astronomical world like a shockwave. If the calculations held true, humanity was witnessing only the third confirmed arrival from beyond our solar system. The first had been the elongated enigma nicknamed ʻOumuamua in 2017. The second, comet Borisov, followed in 2019. Both ignited heated arguments about their origins and meaning. But this new wanderer was unlike either of them. ʻOumuamua stretched no larger than a football field, and Borisov could be compared to a city block. Early estimates now suggested this latest visitor towered over both. An immense body, several miles in size, carrying frozen relics of a star system so remote that even light would take decades to cross the gulf between us. By chance, the telescope in Chile had opened a doorway into the deep unknown. Within 3 days, observatories on 6 continents swung their instruments toward the same point in the sky, racing to collect every trace of light before the object slipped, away into eternal night. Yet hidden in the data was a revelation, even more staggering, one that shattered assumptions about the very limits of interstellar motion. Imagine standing beside a highway where every car roared past at the speed of a thunderbolt. That was the scale of what astronomers uncovered. This visitor was cutting through space at 36 miles every second. At that pace, a journey from New York to Los Angeles would last less than 2 minutes. A flight that takes a passenger jet 6 hours could be completed by this traveler in the blink of an eye. The measurements stunned the scientific community, shattering every known record for interstellar motion. ʻOumuamua had astonished astronomers by racing at 16 miles per second. Comet Borisov exceeded that with 20. But this new arrival was moving nearly twice as fast as either, rewriting the limits of what seemed possible. What made the speed extraordinary was not simply the number, but the story it revealed. Just as a detective reads the angle of a bullet to learn its past, astronomers could trace the violence behind this object's acceleration. The greater the velocity, the more cataclysmic the force that had thrown it into the void. This visitor was moving with what scientists call hyperbolic velocity, the speed of true escape. Imagine hurling a stone so forcefully that it not only breaks free of Earth, but sails beyond the reach of our sun forever. Such energy could only have come from a disaster of extraordinary proportions. A cosmic upheaval powerful enough to fling worlds and fragments into the endless dark. And now one of those fragments was passing through our skies. Its incredible pace came with a price: time. Unlike asteroids that circle the sun for countless millennia, giving generations of scientists a chance to observe, interstellar travelers are brief apparitions. At 36 miles per second, this visitor would sweep across our entire solar system in less than 2 years, offering only a few fleeting months for humanity to gather its secrets before it was gone. Telescopes across the globe fell into urgency. Night after night became a race, each hour of observation a treasure. It was nothing less than a scientific gold rush, as researchers fought to capture every photon of light from the ancient wanderer before it vanished back into the infinite dark. But speed was not its only mystery. Its path across the heavens revealed something even more astonishing. When astronomers retraced the object's journey, following its line through time, they uncovered a truth that left even seasoned scientists without words. This was no stray from the outer edge of our system. It had crossed the abyss itself, millions of years of silent travel through the desolate void between the stars, surviving where nothing should endure. The evidence rested on a single, elegant idea in celestial mechanics: orbital eccentricity. Think of it as the fingerprint of a cosmic traveler, a number that reveals where an object truly belongs. Anything born within our solar system has an eccentricity below 1, tracing closed loops around the sun in endless repetition. But an object from beyond, from the great ocean between stars, carries an eccentricity above 1, following a path that will never return. Our mysterious guest registered an eccentricity of 6.2. The figure may sound modest, but in orbital terms it was astonishing. ʻOumuamua had measured 1.2, comet Borisov 3.6. This newcomer shattered both records, following the most open, hyperbolic trajectory ever observed. In other words, it was more undeniably interstellar than anything we had seen before. When scientists ran the numbers backward, the results were even more striking. The calculations pointed to the direction of the constellation Sagittarius, as though the object had crossed half the galaxy with deliberate precision, threading its way past the pull of countless suns. Still, proof required more than equations. Astronomers had to confirm that no matter how close this visitor came to the sun, even if it skimmed through the outer layers of the corona, its velocity would always remain too great to be trapped. The verdict was clear: nothing in our solar system could hold it. What followed was an extraordinary act of cosmic forensics. Observatories around the world gathered measurements of its speed and position, point by point, building a detailed reconstruction of its trajectory. With every observation, the case grew stronger. Humanity was watching the fastest confirmed interstellar object ever discovered. Within weeks, the International Astronomical Union gave the visitor an official name: 3I Atlas. The 3I marked it as only the third recognized interstellar object in history, while Atlas honored the Chilean telescope that first caught sight of it. Yet the story did not end with its orbit. If its path proved its alien origin, its scale revealed its true majesty. Compared to it, earlier interstellar guests were mere curiosities. ʻOumuamua was the size of a football field. Borisov could be likened to a city block. But early estimates of Atlas suggested a body 6 to 12 miles across. A genuine giant by every measure. Standing beside such a visitor, humanity would be as small as ants gazing up at a towering cathedral of stone and ice. A monument carried across the galaxy by forces older than Earth itself. This new arrival was no pebble from the void. It was the scale of an entire city, sprawling outward like suburbs stretching past the horizon. Determining its size required detective work as subtle as anything out of Sherlock Holmes. Because astronomers cannot measure objects billions of miles away with a ruler, they turn to light itself as the tool. By studying how much sunlight the traveler reflected, and comparing that brightness to its changing distance from Earth and the Sun, they could infer its surface area and approximate scale. The Hubble Space Telescope offered the sharpest glimpse yet, capturing an image that revealed a luminous teardrop. A brilliant core shrouded in a halo of dust and gas. This glowing veil, known as a coma, stretched across thousands of miles. But at its heart lay a solid body of rock and ice, a fragment of another star system that had endured a journey no smaller object could have survived. Why does size matter so much? Because the void between stars is not empty. It is filled with a constant, invisible storm of radiation. a cosmic sandblasting that erodes anything left exposed for long enough. Over millions of years, fragile wanderers are stripped away grain by grain until nothing remains. But this giant's immense bulk had allowed it to weather that storm, shedding only its outer layers while keeping its heart intact. What we were seeing, the stream of dust trailing away from the nucleus, was matter born in a foreign star system, now mingling with particles from our own sun. Its sheer mass also hinted at the violent forces that had expelled it from its home. To fling an object this large into interstellar space requires titanic events, gravitational slingshots from giant planets, or the cataclysm of a dying star hurling fragments outward with the power of worlds. Yet the most astonishing fact was not its size, but its rarity. Finding an interstellar object at all is like pulling a single needle from a haystack that stretches across the universe. In all of human history, across thousands of years of watching the heavens, only 3 such travelers had ever been confirmed. Fewer, in fact, than the number of humans who have walked upon the moon. Each detection is a discovery on par with charting a new continent, a reminder of how vast and empty the cosmos is. Our galaxy alone holds more than 400 billion stars, many with their own planets and comets. And yet, in all that immensity, only 3 wanderers have ever passed close enough for us to notice. Logic suggests that every planetary system should constantly fling comets and asteroids into the void, filling interstellar space with a steady tide of wanderers. Yet in reality, catching sight of one demands extraordinary timing and luck. Imagine the universe as a vast, lightless ocean, and our solar system as a small stretch of shoreline. Countless travelers drift past in the darkness, but only a rare few ever cross into the beam of our watchful instruments. Most slip by unseen, too small, too faint, or passing through regions of sky that no telescope happens to be scanning. The 3 confirmed detections we have are likely just the tip of an unseen multitude. For every one discovered, thousands more have ghosted silently through our neighborhood, leaving no trace. Each confirmed visitor is therefore not just a discovery, but proof of how far our tools have advanced. ʻOumuamua was revealed by the Pan-STARRS telescope in Hawaii, built to sweep vast swathes of sky in search of moving objects. Comet Borisov came to light through the dedication of amateur astronomer Gennady Borisov, using equipment that only recently became accessible to non-professionals. And the newest arrival was detected by Atlas, a planetary defense network designed to guard Earth from dangerous asteroids. Their rarity adds urgency. While stars and planets remain visible for centuries, interstellar visitors grant only the briefest glimpse. By the time we spot them, they are already fleeing at impossible speeds. Scientists have only months, sometimes mere weeks, to gather the data before the object vanishes forever. Every image, every spectrum of light, every radar echo becomes priceless evidence, an irreplaceable sample of conditions from a star system we may never see again. In a sense, this is archaeology among the stars, using fragments of ancient systems that drift to us across unimaginable distances. Together, the 3 known interstellar travelers form a kind of cosmic trinity, each one belonging to a different class. ʻOumuamua, enigmatic and silent, behaved more like an asteroid. Borisov was unmistakably cometary, its tail marking its passage. But this new arrival was something else entirely, where ʻOumuamua concealed itself, revealing almost nothing, no dust, no vapor, not even the shape of its body with certainty. This newcomer was the opposite. It was an exhibitionist on the grandest scale, announcing its presence with spectacle. Within days of its discovery, telescopes picked up the unmistakable signs of cometary activity. A luminous halo or coma bloomed around its icy heart, and a faint tail unfurled as solar heat freed gas and dust into space. The contrast between these 2 travelers was like comparing a sealed vault to an open book. ʻOumuamua guarded its secrets behind a featureless, reddish surface, revealing almost nothing of its true nature. Our new visitor, by contrast, revealed itself freely. With every burst of gas and stream of dust, it offered direct samples of its interior, as though scattering pages from a story written in another world. Spectroscopic studies captured water vapor, carbon compounds, and complex organic molecules spilling into space. These were not random traces. They were chemical signatures carrying memories of the star system where this object was born. The presence of water told us it had formed in a realm cold enough for ice to endure. The organics hinted at chemistry not unlike the processes that shaped the earliest chapters of our own solar system's history. Its behavior only deepened the contrast. ʻOumuamua's strange acceleration sparked speculation that ranged from hidden jets of gas to even wilder theories of alien engineering. But this new comet obeyed the textbook perfectly. Its motion matched what our models predicted: ices sublimating under sunlight, dust trailing behind, acceleration following natural law. Timing, too, was in our favor. ʻOumuamua had slipped through our view only as it was already escaping, leaving scientists mere weeks before it vanished into darkness. This new visitor, however, was discovered on its inbound journey. That gave astronomers months to observe, track, and study it as it grew brighter and more active with each step closer to the sun. The difference in communication was perhaps the most profound. ʻOumuamua had whispered, leaving questions unanswered. This comet shouted. Every molecule cast off into the void was a message, written in the chemical alphabet of a distant system. Astronomers became detectives at a crime scene billions of miles away, reconstructing an origin story millions of years in the making. Each spectral line acted as a fingerprint, proof that this was not just debris, but a relic forged under alien skies. Water vapor dominated the emissions, evidence of a birthplace locked in permanent frost. Alongside it came carbon monoxide, carbon dioxide, and a suite of organic compounds, all pointing to a rich and complex environment of formation. These molecules were more than curiosities. They were like strands of cosmic DNA, encoding the conditions of their creation. Ratios of isotopes within the water could reveal the temperatures and pressures of its ancient nursery. The organics, in turn, mapped out the chemical reactions that unfolded in that forgotten system. What made these results extraordinary was not just what they contained, but their clarity. For the first time, scientists were able to read the chemical script of an interstellar comet with remarkable precision, a script written in the heart of another star's domain and carried across the gulf of space to our waiting instruments. Unlike the distant silhouettes of exoplanets, where scientists must tease out faint chemical fingerprints hidden in starlight, this time we had something far more direct. Raw samples streaming past our telescopes. Each molecule of gas, each drifting grain of dust, was untouched cargo from another star system, preserved for millions of years in the deep freeze of interstellar space. Chemical analysis soon revealed more than anyone expected. In theory, cosmic radiation should have slowly transformed the surface during its long voyage between stars, altering or even erasing the original chemistry. Yet the emissions suggested a different truth. Beneath a thin weathered crust, the interior remained remarkably pristine. The size of the object had granted it protection, shielding its heart from the relentless bombardment of cosmic rays. Still, traces of radiation were there, not as destruction, but as markers. Certain molecules had been split or reshaped into forms that do not occur naturally on planets. These radiation-forged compounds acted like timestamps, preserving a record of how long this traveler had been drifting through the void before arriving in our solar system. The investigation became a live experiment in planetary forensics, unfolding in real time. With every passing week, more observatories joined the campaign, expanding the chemical catalogue into a detailed portrait of alien chemistry. Then came the revelation that stunned even the most cautious astronomers. When its trajectory was carefully mapped, the comet's path through our solar system seemed almost choreographed. Orbital mechanics rarely allow coincidences, yet this object was threading its way with uncanny precision. It would pass near multiple planets at just the right distances for optimal observation, while carefully avoiding close encounters that might alter its flight. The scale of this alignment was staggering. Our solar system spans billions of miles, its planets scattered like islands in a cosmic sea. For an interstellar traveler to weave through these gravitational shoals and still present itself so perfectly to our instruments bordered on the miraculous. Even more remarkable was the viewing geometry. Throughout its approach to the sun, the object would remain visible for months, never lost in solar glare or hidden by daylight. Nature itself seemed to have scheduled the show for human eyes, and when it finally reached its closest passage to the sun, the timing could not have been better. Autumn, when observatories in both hemispheres were primed to work in concert. For astronomers, it was as though the universe had delivered a visitor on a silver platter, a cosmic messenger not only from another star system, but arriving on a trajectory designed for discovery. Professional and amateur astronomers across the globe suddenly found themselves united in anticipation. The comet's path offered clear, extended viewing during the height of observing season, a gift few in the astronomical community took for granted. Even more extraordinary, its trajectory created a natural laboratory. As the object drifted closer to the Sun, astronomers could track its transformation in real time. Ice awakening, dust lifting into space, the tail stretching ever longer like a banner unfurling across the stars. What in textbooks might be a line of equations was now unfolding on a planetary scale before human eyes. Yet in private conversations, some researchers admitted the thought that nagged them. Could such perfect conditions really be a coincidence? The timing, the angle, the months of uninterrupted visibility. The comet seemed almost too well arranged for scientific study, but to venture beyond coincidence was to step into speculation most professionals avoided. Orbital analysis revealed one more sobering truth. This was not a recurring visitor. Unlike periodic comets that loop back every few decades, this object was on a one-way escape trajectory, destined to leave our solar system forever. It would not return. At 4.5 astronomical units from the Sun, the distance of Jupiter's orbit, the magic began. Solar radiation, accumulated over millions of miles, finally reached the threshold needed to stir ice that had lain locked in darkness since before human history. The awakening was like watching spring arrive across an entire frozen world, its surface breathing for the first time in countless ages. The physics were familiar yet profound. Sunlight did more than warm the surface. It delivered energy in precise quanta, snapping molecular bonds that held ice crystals together. With every bond broken, water vapor escaped, dragging tiny grains of dust into space like leaves caught on a cosmic breeze. But these were no ordinary ices. They had formed around another star entirely, under conditions that prevailed when our own solar system was still a swirling disk of gas and stone. The moment represented a rare kind of meeting. Matter from one stellar nursery awakening beneath the light of another, separated by distances so vast that even light itself requires decades to cross them. At first, only a few molecules seeped from the sunlit face of the nucleus, a tentative whisper into the void. But as the comet drew closer, solar heating surged, and sublimation grew not gradually but exponentially, a frozen relic accelerating into life under the fire of a foreign sun. What began as faint, invisible wisps of gas soon swelled into streams detectable by powerful telescopes, then into clouds vast enough to engulf entire planets. At the heart of it all lay the nucleus, a dirty snowball the size of a small city, built from ancient ice, rocky debris, and complex organic compounds. As surface layers vaporized, fresh material beneath was exposed, feeding a continuous cycle of sublimation and dust release. Before our very eyes, the object was evaporating, shedding thousands of tons of material each day. This awakening gave rise to the unmistakable hallmark of comets, the tail. The relentless solar wind, a constant stream of charged particles from the Sun, swept the released gases and dust into space, sculpting not one, but two distinct trails. One, formed of ionized gas, glowed in ghostly blue. The other, made of dust grains, shone with the soft yellow light of reflected sunlight. Together, they served as living proof of the transformation underway. Each new image captured a slightly different portrait, a time-lapse of ice turning into vapor, matter unraveling across the stars. Then came Hubble's unblinking gaze. When the space telescope turned its instruments toward this interstellar traveler, it captured something unprecedented. The sharpest, clearest image of an object from beyond our solar system ever obtained. Where ground-based observatories had shown only a smudge of light, Hubble revealed astonishing structure. At the image's center burned a brilliant point, the hidden nucleus, veiled in its glowing shroud. Around it, streams of gas and dust fanned outward like frozen fireworks, each jet tracing the invisible physics that sculpted this ancient wanderer. The overall form was unmistakable, a teardrop, asymmetrical and graceful, its long taper pointing away from the Sun. That shape alone told the story of two competing forces: solar radiation pushing material outward, while the faint gravity of the nucleus fought, and failed, to hold it back. Even more extraordinary, Hubble caught clear evidence of active sublimation in real time. Bright jets burst from isolated regions of the nucleus, spraying fountains of vapor and dust into space. These jets shifted as the object rotated, suggesting surface patches rich in ice or angled perfectly towards sunlight. From these images, scientists refined their calculations. By comparing the brightness of the nucleus to its surrounding coma, they concluded the solid core was between 1 and 3 miles across, larger than the enigmatic ʻOumuamua, though still smaller than many of the comets native to our system. But beyond size, Hubble's picture became something timeless, a historical document. This was humanity's clearest look yet at unaltered matter from another star system, an alien relic preserved in exquisite detail for generations to come, flowing behind it like a cosmic wedding veil. The tale carried the true meaning of this discovery. It was more than a beautiful plume of light. It was a written record of the object's history, etched across millions of miles of space. Each particle within it had been sealed away for billions of years, only now released, scattered across our solar system like breadcrumbs from a world that circled another sun. Spectroscopic analysis of the comet's tail revealed a wealth of information about its origins. Different regions glowed with distinct hues, each a chemical signature written in light. Bands of blue marked ionized gases such as carbon monoxide, energized by solar radiation. Yellow and red regions shone with sunlight, reflecting off dust grains of varying sizes and composition. Even the tail's structure carried meaning. As the comet rotated, alternating surface regions faced the sun, sublimating at different rates. This rotation created spiral patterns within the tail, like water spraying from a spinning garden sprinkler. Patterns that allowed scientists to calculate its rotation period and identify the active zones on its surface. The tail was more than a spectacle. It acted as a fossil record unfolding in real time. The oldest particles, expelled weeks earlier, had been pushed farthest away by solar wind and radiation pressure, while the newest grains remained near the nucleus. The result was a temporal map of activity stretching across millions of miles. The distribution of particle sizes told another story. Larger grains suggested rocky debris embedded within the ice, while the finer dust hinted at delicate material gathered during the comet's original formation. Most remarkable of all, some of these grains contained intact organic compounds, survivors of both the comet's birth and its million-year interstellar journey. These molecules offered direct, laboratory-ready samples of alien chemistry from a distant planetary system. At roughly 2 astronomical units from the Sun, extraordinary changes began. Gentle solar heating gave way to a cosmic blowtorch. The quiet sublimation of ice transformed into a furious cascade of gas and dust, with the comet releasing thousands of tons every hour. What had been a simmering ember now flared like a bonfire on a planetary scale. The physics behind this awakening involved more than simple warming. Solar radiation carries momentum as well as energy. With billions of photons striking the comet each second, radiation pressure acted like an invisible hand, sweeping material from the surface at hundreds of miles per hour. The process was far from uniform. Different ices vaporize at different thresholds. Water begins around 3 astronomical units from the Sun, while carbon monoxide and other volatile compounds begin far earlier. This created layers of activity that intensified as the comet drew closer. Picture the nucleus as a dirty iceberg adrift in space, slowly rotating beneath a relentless heat lamp that grows hotter every day. Occasionally, subsurface reservoirs of volatile materials breached the surface, erupting in jets of gas and dust that stretched thousands of miles into space. These spectacular plumes, visible even through modest backyard telescopes, were geological events unfolding in real time on a body billions of miles away. The solar wind added yet another layer of complexity. As the stream of charged particles collided with the comet's expanding coma, shockwaves rippled outward, sculpting the tail into shifting patterns of turbulence and order. The intensification also created dazzling visual displays. What began as a distant, dim speck of ice now shone as a beacon across interplanetary distances. The interstellar wanderer was no longer silent. It blazed in glory as it neared the most perilous stage of its journey. As Earth entered autumn, the comet reached its moment of greatest risk and splendor. Perihelion, its closest approach to the Sun. This would be both the climax of its performance and, perhaps, the moment of its destruction. At a distance of just 130 million miles from the Sun, The interstellar traveler entered a crucible of unimaginable heat, temperatures so intense they could vaporize even rock and metal. For an object that had drifted through the frozen silence between stars, this was a trial of survival. Its trajectory became a kind of cosmic gamble, gravity pulling to capture it, while its staggering velocity fought to carry it past the solar inferno and back into the dark expanse of interstellar space. Calculations confirmed it would ultimately escape, but not without a heavy toll. Vast layers of its material would be stripped away. As the weeks of October passed, the sublimation accelerated beyond measure. What had once been a delicate trickle of gas and dust erupted into a furious torrent, streaming from the nucleus at thousands of miles per hour. The coma expanded to colossal dimensions, growing larger than entire planets, and turning the object into a blazing spectacle visible across the night sky. But with the beauty came violence. Subsurface reservoirs of ice burst open in explosive outbursts, releasing jets of gas and dust with energies rivaling nuclear detonations. Photographs captured sudden flashes of brilliance, the signs of geological upheavals on a scale beyond earthly comprehension. Each eruption hurled debris across thousands of miles, reshaping the traveler with every passing moment. To imagine this passage is to picture an ice sculpture sprinting through the heart of a blast furnace. The outer layers inevitably melt and boil away. Yet if the core remains strong and the dash through fire swift enough, something of its essence might endure. For astronomers, this was both triumph and heartbreak. The comet's fury made it more visible than ever, providing a wealth of data on interstellar composition. But with each sunrise, its brilliance drew closer to the sun's blinding glare, threatening to erase it from view. The October encounter was the fulcrum of its fate. Would it survive the sun's embrace and return to the void, or would it crumble into fragments like countless messengers before it? To answer this, scientists embarked on one of humanity's most ambitious quests, tracing the wanderer's origin across billions of years. This was not simply mathematics, but a form of cosmic archaeology. By rewinding the paths of stars in our galactic neighborhood and accounting for gravitational nudges across deep time, astronomers tried to reconstruct where this traveler was born. The task was akin to finding the birthplace of a single raindrop by tracing its path back through a hurricane. Stars drift through the galaxy in tangled, shifting patterns, shaped by spiral arms, stellar flybys, and the vast gravity of billions of suns. Over millions of years, even tiny perturbations accumulate into sweeping changes of motion. With the help of supercomputers, observatories around the world began simulating these movements, charting where neighboring stars had once been when this object first set out on its journey. Each calculation spanned distances measured in light years and timescales longer than the history of complex life on Earth. The first results left scientists stunned. Backward projections showed that this interstellar wanderer had been adrift for at least 4 million years, perhaps far longer. In that time, it had crossed gulfs of space so immense that even light, the fastest thing in the universe, would need decades to cover the same distances. This was not merely a visitor from another star. It was a time traveler, carrying matter from an age when early humans were only just beginning to rise and walk upon the Earth. Even more astonishing was the fact that it had survived its passage. For millions of years, it had threaded its way between stars, weaving past gravitational hazards that could have flung it into oblivion or shattered it outright. That it arrived intact suggested a streak of unimaginable fortune, or perhaps a trajectory shielded from violent disruptions by cosmic chance. The search for its birthplace narrowed to regions dense with stars, where gravity's constant jostling creates cosmic billiard tables. In such crowded neighborhoods, stars can steal and scatter planets, comets, and debris across the galaxy. Among the most likely parents were ancient red dwarf systems, small, long-lived suns whose planets and icy belts might have remained stable for billions of years until a wandering star passed too close. That fleeting encounter could have delivered the slingshot of gravity strong enough to cast this fragment loose, setting it on its interstellar odyssey. Yet, the investigation carried a sobering reminder. For every one of these wanderers we glimpse, millions more likely sweep silently through our solar system, unseen, their paths never close enough to Earth for telescopes to catch. The rarity of detection makes each discovery priceless, a message from the unknown carried on a single grain of ancient ice. But the true marvel lay not only in its origin, but in its endurance. The spaces between stars are deserts of almost unimaginable hostility. Temperatures hover just above absolute zero. Cosmic radiation, unshielded by atmospheres or magnetic fields, scours every exposed surface. The nearest warmth, the nearest light, lies trillions of miles away. To survive here is not merely to drift. It is to endure across ages that dwarf the rise and fall of species and civilizations alike. This was not a casual voyage between neighboring worlds. It was an odyssey measured in geological time, a journey across a wilderness where survival is the rarest of miracles. To grasp its meaning, we must lay out the timeline of this extraordinary crossing. When this comet first slipped free into the void between stars, Earth itself was still unrecognizable. Continents were only beginning to take shape. The seas were barren of anything more complex than single-celled life. In the time it took this frozen messenger to drift from one stellar neighborhood to another, entire mountain ranges had risen, eroded, and vanished upon our planet's surface. Its survival challenges were beyond anything life on Earth has ever endured. For millions of years it faced a relentless hail of cosmic rays, particles hurled to near light speed by the explosions of distant suns. Each impact rewrote its surface chemistry, breaking apart fragile molecules, forging strange new compounds unknown anywhere else in nature. The interstellar gulf was no empty silence, but a storm of dust grains and stray atoms. At the velocity of our traveler, each encounter struck like a microscopic bullet. Imagine driving through a sandstorm at highway speeds, except this storm stretched across light years, and the journey lasted for millions upon millions of years. Cold was its constant companion. With no nearby star to lend warmth, the comet's surface sank to temperatures just above absolute zero. At such extremes, even the strongest materials grow brittle as glass. A single collision could have shattered it like crystal. Yet somehow it endured. When it finally reached our solar system and erupted into a coma of gas and dust, it proved that vast reserves of volatile ices had survived intact across the unimaginable gulf. This suggested either extraordinary luck or hidden structures within that shielded its core from the endless hostility of interstellar space. Its odyssey was not only a battle against radiation, cold, and impact. It was a constant dance with gravity. Every passing star, every drifting mass in the galaxy tugged at its path. A close encounter might have hurled it onto a new trajectory, slowed it into capture, or shattered it entirely. Over 4 million years, these influences should have erased its course into chaos. Yet it arrived to us, coherent, whole enough to display its beauty. Every faint wisp of vapor rising from its nucleus told this survival story. Each molecule of gas was a relic, matter that had endured the longest and harshest journey a fragment of rock and ice could ever take. The very velocity of the comet, that blistering 36 kilometers per second, was more than a measurement. It was a kind of biography, written in the precise language of physics. Its speed carried the scars of the violent event that had cast it loose, and the subtle signatures of gravitational encounters across millions of years. Astronomers, like forensic investigators at a cosmic crime scene, could read these details in its trajectory. Interstellar velocities are not the result of gentle drifting. They are born of catastrophe, a planet torn apart, a star's gravity slingshotting fragments into exile, or a system's upheaval flinging worlds and ice into the eternal dark. Our visitor was a survivor of such an event, still carrying in its motion the record of its violent birth. The energy required to accelerate something the size of a mountain to 36 kilometers per second is almost beyond comprehension. Only the most violent encounters in the universe can produce such speeds. The close tug of giant planets, the slingshot of binary stars, or the shockwave of stellar explosions powerful enough to sterilize entire systems. Velocity, in this sense, is not just a number. It is a signature, a fossil of the environment that cast the object adrift. Different stellar neighborhoods leave different imprints on their exiles. Young systems, brimming with massive planets and chaotic orbits, tend to hurl fragments outward with tremendous force. Older, quieter systems send their wanderers away more gently. The blistering speed of our visitor suggested birth in a restless, turbulent region of the galaxy. Think of interstellar space as a vast highway with shifting speed limits. Some travelers creep slowly from nearby stars, while others, like this one, streak across gulfs of light years at breakneck pace, their origin marked by chaos and upheaval. Speed even carries timing information. Faster wanderers cross the interstellar desert more quickly, their journeys measured in millions rather than billions of years. Our visitor's pace suggested an ejection only a few million years ago, fresh by the standards of cosmic history. But speed alone does not tell the whole story. Direction matters too. By tracing the trajectory backward and correcting for the motions of nearby stars, astronomers could narrow the list of possible parent systems. The precision required was staggering. A difference of even a single meter per second in measured speed could shift the candidate origin by dozens of light years, moving it into entirely different stellar neighborhoods. Yet the greatest revelation came not from its motion, but from its chemistry. As the sun's warmth freed ancient ices into vapor, spectroscopic analysis revealed element ratios unlike those of comets born in our own galactic suburb. The fingerprints pointed instead to a population of stars older than the Milky Way's spiral arms, stars forged in an era when the galaxy was still young and poor in heavy elements. Astronomers call this region the thick disk, a vast, mysterious structure of ancient suns, whose orbits carry them high above and below the galactic plane. These stars are relics from the early days of our galaxy, long before it was enriched by countless generations of stellar deaths. And it was from this environment, billions of years ago, that our visitor first condensed into ice and stone. Imagine it, grains of dust and frozen molecules gathering around a faint, metal-poor star when the Milky Way was less than half its current age. That fragile nucleus then endured billions of years of quiet orbit, until some gravitational upheaval cast it loose into the interstellar dark. Now, warmed by our own sun, it carried across space the unbroken memory of that ancient epoch, a frozen biography from one of the oldest neighborhoods in the galaxy. Such movement through the galaxy increases the chances of close gravitational encounters, interactions powerful enough to fling planetary debris into the void between stars. Yet stars belonging to the galaxy's thick disk are generally more settled than their younger counterparts. Over billions of years, they have stabilized into predictable paths, making such violent ejections relatively uncommon. For our visitor to have broken free from such a system, something extraordinary must have occurred, either a rare and dramatic gravitational upheaval or a far stranger mechanism. Some astronomers suggest that binary stars, two suns orbiting one another, can produce complex gravitational patterns strong enough to hurl nearby objects outward at astonishing speeds. Others propose encounters with wandering planets or faint brown dwarfs, cosmic drifters that occasionally pass through established star systems like wrecking balls, disrupting everything in their path. This connection to the thick disk also hints at the deep age of the traveler. If it was born around one of these ancient stars, it could be a fragment of some of the oldest matter preserved in our region of the galaxy. Its chemistry would carry the fingerprints of a universe that looked very different from the one we know today. That record was not only hidden in its chemical makeup, but etched into its very surface. For millions of years, tiny invisible projectiles, cosmic radiation, had been bombarding it endlessly, atom by atom. These high-energy particles, accelerated by exploding stars, black holes, and other violent events, strike with enough force to shatter molecular bonds and forge entirely new compounds. Over eons, every inch of its surface had been struck by countless billions of these particles, like an endless sandblasting by an invisible storm. The result is what scientists call a space-weathered surface. Under a microscope, such terrain reveals glassy beads, metallic dust, and crystals fractured by radiation. These features serve as natural clocks, recording the length and severity of the object's time adrift. Cosmic ray damage is like erosion on Earth, but operating on molecules instead of mountains, and driven by some of the most energetic forces in existence. This weathering also helps explain the comet's curious behavior. Surfaces shaped by radiation respond differently to sunlight and solar wind, influencing how gas escapes, how dust forms, and even how brightly the object glows. Spectroscopic studies confirmed these scars of interstellar travel, revealing strange molecules and unusual isotopes that could only have formed under such bombardment. The damage, however, was not uniform. Some regions had been shielded by layers of material, while others were exposed directly to space, creating a patchwork of altered and preserved zones. These differences determined how and where the surface reacted once heated by our sun. Most astonishing of all, the very weathering that scarred the exterior had forged a hardened crust, an accidental shield that preserved the untouched interior for billions of years. The altered surface materials had created a hardened barrier, slowing the sun's heat from reaching the deeper layers and shielding it from constant micrometeorite strikes. Yet this protective shell could not guard its secrets forever. As solar energy crept further inward, it began to expose materials untouched for millions of years. Fragments of a past preserved since the object first left its home star. Across the silent reaches of interstellar space, uncountable travelers move along invisible highways we are only beginning to recognize. The discovery of this third confirmed visitor was both astonishing and humbling, for it underscored a sobering truth. Our instruments capture only the faintest trace of this endless traffic. For every object we manage to detect, thousands more likely slip past unseen, hidden by their speed, their darkness, or the blind spots in our observation. The difficulty lies in their nature. Most interstellar bodies are small, cold, and dark, reflecting almost no light until they drift close enough to a star for solar heat to awaken them. By the time they reveal themselves, they are often already racing outward again, leaving only a brief window for study. Even then, detection is a matter of perspective. Our telescopes can monitor only slices of the sky at once, leaving vast regions unobserved. It is like trying to measure highway traffic by staring through a keyhole. The view is real, but painfully incomplete. Imagine interstellar space as an immense ocean. Most ships cross it on routes far from any shore, their sails hidden in the night. Only the rare few drift near our coast, or shine brightly enough to be glimpsed from afar, allowing us to notice them before they vanish again into the dark. Speed makes the challenge even more daunting. At 36 miles per second, an object can traverse the breadth of our solar system in under 2 years. If spotted late, astronomers may have only weeks, or even days, to gather data before the traveler fades beyond reach, swallowed once more by interstellar space. Recent advances have improved our odds. Modern automated survey telescopes, like the Chilean instrument that revealed this visitor, now scan vast areas of the heavens simultaneously, dramatically increasing our chances of catching these fleeting messengers. Still, no system is perfect. Objects approaching from the direction of the sun remain hidden until they are already retreating. Others slip by disguised against the crowded backdrop of distant stars, camouflaged in the cosmic harbor. The truth is sobering. We have officially detected only 3 interstellar visitors in all of human history. Logic suggests that dozens, perhaps hundreds, have already passed through our neighborhood without notice, each carrying clues about alien star systems, each an unrepeatable chance for discovery. What have we missed? What secrets still drift unseen just beyond the reach of our technology? Each of the 3 we have observed has told a very different story. ʻOumuamua, the first, arrived as a riddle, an object that refused to fit any category we understood, reddish and silent, defying all expectations of what a visitor from another world should look like. Its elongated shape, unexplained acceleration, and absence of visible outgassing made ʻOumuamua the ultimate cosmic riddle, an object that continues to defy explanation. By contrast, Comet Borisov behaved exactly as astronomers expected, serving as the textbook interstellar ambassador. It displayed every hallmark of a familiar comet: a distinct nucleus, a surrounding coma, a luminous tail streaming away from the sun, and chemical signatures nearly identical to those seen in our own system. Our current visitor, however, is something altogether different. A true giant, it dwarfs both predecessors while producing activity on a scale far beyond anything previously observed. Where ʻOumuamua stretched no longer than a football field and Borisov measured about the size of a city block, this newcomer spans several miles, an order of magnitude larger. The contrast in size alone hints at radically different origins. Small wanderers like ʻOumuamua may be fragments dislodged by relatively mild encounters. Mid-sized travelers, such as Borisov, likely represent more typical comets expelled during the chaotic birth of planetary systems. But massive objects like our present guest demand far more violent forces, catastrophic events capable of flinging entire mountains of ice and rock into the void. Together, these 3 discoveries resemble artifacts from alien civilizations, each carrying clues about the conditions of their home systems, the forces that launched them into interstellar space, and the challenges they endured on their journeys across the galaxy. Their behaviors reveal equally striking differences. ʻOumuamua remained almost entirely inert, withholding details about its composition. Borisov showed modest activity, releasing enough gas and dust to confirm its cometary nature. But the new arrival erupted into a spectacle, venting such vast clouds of material that telescopes across the world could track it with ease. Speed added another dimension to their stories. ʻOumuamua's modest velocity suggested origins relatively close to our stellar neighborhood. Borisov's intermediate pace hinted at more distant routes. The extraordinary velocity of our current visitor, however, pointed to origins in turbulent regions where gravitational encounters are fierce and dynamic. Each discovery also marked a leap forward in our own observational ability. Every molecule released from this nucleus carried a chemical record from another star system, an autobiography written in the language of atoms. Unlike exoplanet studies, where data comes filtered through atmospheres and starlight, these interstellar visitors offered unmediated samples, pristine fragments of alien chemistry. Water dominated the emissions, but isotopic analysis revealed it was not identical to terrestrial water. The subtle ratio differences between heavy and light hydrogen atoms offered direct clues about the temperatures and pressures of the environment where this ice first condensed. These isotopic fingerprints functioned like cosmic DNA, linking the object back to its stellar birthplace. Carbon compounds added further chapters to its biography. Scientists detected carbon monoxide, carbon dioxide, and a suite of organic molecules, signatures of formation in a rich chemical environment, perhaps a debris disk around a young star. Locked away in deep freeze for millions of years, these substances preserved conditions from an ancient time when alien worlds were first coalescing. The nucleus of the visitor was like a geological core sample from another solar system, its layers recording different eras of chemical history. As sunlight penetrated deeper, it revealed material shielded for eons from cosmic radiation, material still pristine after its interstellar crossing. Most intriguing of all were the organic compounds. Their presence suggested that the same kinds of chemistry that shaped the early history of our own solar system might also be common elsewhere. Complex carbon-based molecules require precise conditions, time, temperature, and protection from destructive radiation. Some of the species identified in this visitor could only have formed through slow, patient processes stretching across geological time. The chemistry revealed that this visitor did not come from a young and chaotic stellar nursery, but from a stable, mature system that had time to cultivate intricate chemistry. The ratios of metals within its gases pointed to a parent star enriched by multiple generations of stellar death and rebirth, much like the environment in which our own solar system once emerged. Even more extraordinary, several detected compounds bore the unmistakable marks of cosmic radiation endured during the object's long voyage. These radiation-shaped molecules acted like natural clocks, recording how long the traveler had drifted between the stars. For the first time, astronomers were practicing a kind of chemical archaeology on matter born in another corner of the galaxy. Across the world, the scientific community treated the event with urgent intensity. Telescopes on 6 continents raced against time to gather every photon of light before the visitor slipped from view. The effort resembled an archaeological excavation, where the artifacts were crumbling even as researchers tried to preserve them. Each day brought the comet closer to solar conjunction, when the sun's glare would hide it for months. By the time it re-emerged, it would already be receding into the depths of space, fading rapidly with every passing hour. In response, observatories everywhere reorganized priorities. Directors cancelled scheduled projects to give astronomers precious hours of tracking. Even the Hubble Space Telescope, normally reserved years in advance, granted emergency access to capture images at the highest possible resolution. From the peaks of Chile to the volcanic slopes of Hawaii, ground-based facilities coordinated shifts, handing the target from one hemisphere to the other as Earth rotated. Amateur astronomers, armed with sensitive digital cameras, joined the campaign with surprising effectiveness. Their images filled crucial gaps, confirming and supplementing professional data. Together, this global effort became a scientific relay race. Each telescope, whether massive or modest, passing along pieces of a puzzle that revealed the story of an ancient traveler from beyond the stars. Optical telescopes tracked subtle shifts in brightness and mapped the traveler's path across the backdrop of stars. Infrared instruments traced faint heat radiating from its nucleus, sketching temperature patterns across its surface. Meanwhile, radio observatories tuned into molecular emission lines that betrayed the makeup of gases escaping into space. Each dataset was less a static record and more a fleeting snapshot, capturing a system in constant transformation. Occasionally, the object erupted with sudden outbursts, its brightness surging by factors of 10. These dramatic displays created brief but extraordinary opportunities for study, though they seldom lasted more than a few days or weeks before fading. Adding to the challenge, Earth's own orbit steadily shifted the geometry of observation. As our planet swung around the Sun, the angles of illumination changed, opening and closing narrow observational windows. Even the weather became a decisive factor. Nights of clear skies, normally routine, were now invaluable. Every lost evening meant irretrievable data. To reduce risks, observatories in diverse climates served as backups, ensuring at least one set of eyes could remain on the messenger. Yet the greatest frustration lay in the knowledge that this might be the only chance humanity would ever have to study this particular interstellar wanderer. The visitor hurried towards solar conjunction and eventual obscurity. Scientists began turning their attention to the next opportunity. Plans were already underway for missions designed not to chase, but to wait. The European Space Agency's Comet Interceptor project embodied this new philosophy. A spacecraft placed at a gravitational balance point between Earth and the Sun, lying dormant until the cosmos delivered another guest. Unlike traditional missions, which are launched toward known targets, the interceptor would hold its position, ready to awaken when a suitable traveler was discovered. The approach was akin to keeping a watch station along a busy sea lane, prepared to investigate unfamiliar ships as they pass. Such a mission demanded patience and robust engineering. Systems able to remain idle for years, then activate within days once a target was spotted. Flexibility would be critical. The interceptor would require significant maneuvering ability to pursue objects on unpredictable paths at enormous speeds. Unlike conventional spacecraft, built for well-studied destinations, this probe would need to adapt to anything, from small rocky fragments to large volatile comets. In essence, humanity was preparing for the unknown, laying the groundwork to meet the next emissary from beyond the stars on its own terms. The proposed payloads were science fiction turned into engineering blueprints. Miniaturized instruments would probe surface chemistry, internal layering, magnetic fields, and gas emissions, all crammed into spacecraft small and light enough to reach the extraordinary velocities required for interstellar interception. Every gram of equipment had to justify its place, balancing against the fuel reserves needed for rapid course corrections and high-energy maneuvers. Timing added yet another layer of difficulty. From the moment a new visitor was spotted, teams might have only a few short months to chart trajectories, reprogram navigation, and execute complex orbital changes. Traditional planning cycles measured in years would have to collapse into weeks of non-stop calculation and decision-making. Some concepts envisioned fleets of spacecraft, each playing a role, one racing past the object in a high-speed flyby, while others attempted the near-impossible task of matching speed for a closer rendezvous. This distributed approach would hedge against failure and maximize the scientific yield. The ultimate ambition was bold, moving beyond distant observation and into direct engagement, turning these interstellar wanderers from mysterious flashes in our telescopes into studied emissaries of alien star systems. That such opportunities were appearing at all was no accident. The rise in detections was driven not by luck, but by a technological revolution in skywatching. Barely 2 decades ago, finding a faint, fast-moving object in the outer solar system would have been nearly impossible. Instruments of the time were built to study distant galaxies or nearby planets, not elusive travelers slipping across the night. The breakthrough came with automated all-sky surveys, transforming astronomy from targeted observations into continuous surveillance of the heavens. Programs like the Catalina Sky Survey, Linear, and Atlas now photograph enormous swaths of sky every few nights, comparing fresh images against vast digital archives to flag anything new or in motion. These systems function like cosmic security, cameras, tirelessly monitoring for intruders that reveal themselves only through their subtle shifting trails. Every night, computer algorithms sift through millions of measurements, flagging anomalies for human review. Just 2 decades ago, the sheer processing power required for such tasks would have been unthinkable. Now, modern systems can compare the brightness and positions of millions of stars in minutes, isolating the handful of moving objects hidden among the vast backdrop of still points. What once would have taken months of calculation can now be accomplished almost instantly. Advances in detector technology have been just as transformative. Modern CCD cameras capture light from objects thousands of times fainter than those once, recorded on photographic plates, pushing the boundaries of detection deeper into space. This leap in sensitivity allows astronomers to spot smaller travelers at far greater distances, expanding the surveyed volume of space dramatically. Global coordination has added yet another advantage. When a survey telescope identifies a suspicious object, observatories worldwide can quickly pivot to confirm its trajectory and nature, forming an interconnected web of follow-up coverage. This network effect multiplies the power of individual facilities, ensuring fleeting cosmic visitors are less likely to slip past unseen. Equally important has been the development of new strategies for distinguishing true interstellar visitors from the countless asteroids and comets discovered each year. Only recently have orbital analysis techniques advanced enough to reliably flag hyperbolic paths, trajectories that mark an object as unbound to the Sun. Without these tools, the first interstellar detections would have been lost in the noise. What this revolution has revealed is striking. Interstellar visitors are far more common than once believed. Their apparent rarity was an illusion created by our lack of tools. The galaxy, it turns out, is laced with hidden traffic lanes, gravitational highways that funnel ejected debris between star systems. Far from being an empty void, interstellar space behaves like a vast transportation network. Computer simulations show that once expelled, these objects do not drift randomly. Instead, they follow curved routes shaped by the combined pull of the Milky Way's gravitational field. Much like rivers converging on lowlands, interstellar debris tends to collect along certain predictable channels, where stellar density and gravity guide their flow. Our galaxy can be imagined as a sprawling city, complete with broad avenues, side streets, and long-established traffic patterns. Objects that enter these routes at the right speeds and angles are carried across vast distances, passing star after star along the way. The solar system itself lies at a crossroads of several of these routes. Mapping them requires more than tracking stars as they appear today. It demands projecting their motions millions of years into the future. Stars are not fixed in the sky. They weave through the galaxy in intricate orbits, sometimes drawing closer together, sometimes drifting apart. These shifting positions constantly reshape the interstellar highway system, with some routes carrying heavier traffic than others. Regions dominated by binary star systems, where complex gravitational forces tug relentlessly at orbiting debris, tend to produce far more ejected material than solitary stars. Stellar nurseries too, those turbulent birthplaces of new suns and planets, scatter vast amounts of leftover fragments into interstellar space as young systems take shape. These environments feed the invisible traffic lanes that stretch across the galaxy, and they explain why certain types of interstellar visitors reach us more often than others. Small rocky fragments, requiring little energy to escape their parent systems, are the most common travelers along these routes. By contrast, the giant comets, like our current visitor, are rare jewels, demanding violent ejection mechanisms born from cataclysmic encounters. Understanding these traffic patterns has already begun to shape observatory strategy. By identifying where the hidden highways intersect with our solar system, astronomers can predict the most likely entry points for future wanderers and align telescopes to watch those regions. The long-term vision is bold. To chart a comprehensive map of the galaxy's interstellar transport network, a guide not only for detection, but perhaps someday for missions that could ride these currents to distant stars. What emerges from this work is a view of the Milky Way as a deeply interconnected realm, where material is not locked to its birthplace, but shared across unimaginable distances. Each interstellar visitor offers something no telescope alone can provide: a physical artifact from another star system, one we can measure, analyze, and even hold in laboratory conditions. Unlike traditional astronomy, which relies on decoding the light of distant objects, interstellar archaeology gives us direct access to matter forged under alien suns and preserved in the icy stillness of deep space. The significance stretches far beyond curiosity. These objects are time capsules, carrying chemical fingerprints from epochs when our own planet was unrecognizable. Every isotopic ratio, every molecular compound offers clues about planetary formation, stellar metallicity, and the environmental conditions billions of miles from Earth. Think of the solar system as a cosmic customs station, where visiting cargo from other neighborhoods is inspected with spectrometers and cameras, each scan adding another fragment to the puzzle of galactic diversity. The archaeological metaphor becomes even sharper when we consider timescales. Objects arriving now began their journeys when the skies above Earth were dominated by different stars, and when the chemistry of the interstellar medium bore little resemblance to today's. These wanderers preserve not only material from alien systems, but also records of ancient galactic history itself. Future spacecraft will elevate interstellar archaeology from passive reception to active exploration. Interceptor missions promise close-range studies of structure and surface. Sample return technologies may one day bring fragments of alien comets back to Earth. Landers could be deployed on the largest visitors, unlocking data no remote telescope could ever hope to provide. The field is also transforming the way science itself is conducted. The fleeting windows of observation demand unprecedented levels of international collaboration. Ground observatories, space telescopes, and even amateur astronomers must act in coordinated unison, creating a global framework for rapid response science. These networks are already laying the groundwork for studying even stranger messengers that may soon arrive. Most profoundly, interstellar archaeology has revealed that our galaxy is not a silent void, but a living system of exchange. Material routinely travels between stars, linking planetary systems across the Milky Way with threads of shared chemistry. Far from being isolated, our solar system is part of a vast galactic community connected by unseen highways carrying messages from worlds we may never set foot upon. This emerging discipline is more than a new branch of astronomy. It is the dawn of a perspective that will reshape how we understand planetary origins, stellar life cycles, and our place within the greater cosmic neighborhood.